Alright, welcome back, Year 12 Methods students. Last week on Methods, we were doing differentiation, calculating derivatives. This week, more differentiation. Yes, it goes on, there's lots happening. So today, there's a few things. 9I, we're looking at derivatives of circular functions. Now, again, straight up early in this textbook here, there is a lot of information about the proofs of how we get to these different things. Happy for you, as always, to read how they derive each of these rules. At the end of the day, you don't necessarily need to know the proofs, you just need to know how to run the calculations using obviously the rules. So we're going to skim through these pretty quickly. So again, if you've got the derivative of sine k theta, in this particular case, if you've got the function sine theta, then the derivative of that is cosine theta. Yep. So that's an easy one to remember. Yep. If you have the k value in front of it, obviously that comes out the front, and we'll get onto that in a moment with the rules. There is a proof which says as theta approaches 0, sine theta divided by theta is equal to 1, and that can come in helpful a little bit later on. So as I was saying, yeah, if you've got sine k theta and you are calculating the derivative, that k comes out the front, and obviously this becomes cosine. K theta stays the same in there. Derivative of sine becoming cosine is pretty straightforward. People make more mistakes calculating the derivative of cosine because it's a little bit different. With cosine, when you are calculating the derivative of cosine, it becomes negative sine. Yep. So you do need to not jumble that up. Some people do make that mistake. Obviously, it's costly if you forget that negative when you are getting the derivative of cosine. Again, if you've got cosine k theta, k comes out the front, but remember it's the negative of that. Yep. And it becomes sine k theta. Cool. You can also work out the derivative of tan k theta. Yep. Now, generally speaking, most of the time we're happy with the derivative of tan being equal to what you do need to know, sorry, is there's an extra fun fact, sorry. So if you have 1 over cosine theta, that is also known as sec theta, yep, which is short for secant, yep. Now, given that we know the definition of sec theta is equal to 1 over cosine theta, when you are calculating the derivative of tan k theta, it turns out it is, the k comes out the front and it becomes sec squared k theta. Yep. So you just again need to just know this fact here, and just remember what sec is as well. So remember, sec theta is the same as 1 over cosine theta. Cool. Alright, now that we've got all that out of the way, let's have a look at this stuff here. Finding the derivative with respect to theta for each of these. We've got sine 2 theta. So again, you need to know that the derivative of sine is cosine. There is a k value here. That k value comes out the front, which is the 2, changes to cosine, and we've got obviously k theta part still there. Yep, so derivative of sine 2 theta is 2 cosine 2 theta. Perfect. We're going to tan one. Oh, this is going to be cool. Tan 3 theta. Again, we know that that's the k value. The k comes out the front. As we said before, the derivative of tan is sec squared theta. So in this particular case, the k comes out the front. So we've got 3. It's sec squared. And then we've got the k theta there. which is listed. Yep. So it's really just applying the rule there with that. Cool. Now one of the things as well is when you're writing sec squared 3 theta, for example, it's actually in when you're writing the squared of this here, we don't write it after it at the end here. When you're doing trigonomic equations here, or trigonomic ratios, you write the squared after the ratio, and that'll become a bit clearer here with this one. So let's say you've got sine squared of 2 theta. This is really sine 2 theta squared. Yep, but they don't write the squared after it. It's the squared gets put there. Yep. So in this particular case, where you've got sine squared 2 theta, maybe I can use a pen to illustrate this. Let's see. We'll soon find out, won't we? So here, if you got what, this might work. Y equals sine. No, that's an n. 2 theta. Whoops. Imagine that's a theta. And then you've got the squared here. Let's try squared again. Yep. So we don't write it like this, but really you can see it a bit clearer this way. If you had to apply the chain rule, this here is u squared. Yep, y equals u squared. With this part here being the u part, so that there sine 2 theta would become the u, and that's squared. Yep, even though it's not written like that, that's really what's going on. So given that, okay, let's see if we can get rid of this now. Oh dear. Sorry about this. It takes time. Cool. So given that we've got y is equal to u squared here, you can actually define what u is. U is the sine 2 theta part, applying the chain rule that we learnt the other day. So dy d theta is going to be dy du. So calculating the derivative of that, so 2 comes down the front, 1 away from the power, it's 2u. And then differentiating sine 2 theta, yep, which we can do. Yep. So the k value comes out the front, it becomes cosine 2 theta there. Yep. Alrighty, so applying the chain rule, writing it out, this 2 here gets multiplied with that 2 there. Yep, so that becomes 4. Oop. And so we've got 4u cosine 2 theta. We're going to resubstitute in what u was up here to finish it off. Yep. Again, with these chain rule questions, it's a matter of clearly and carefully setting them out. Yep. I see many students not clearly setting it out, and mistakes are happening. Take your time, write down what u is, write down each of the parts, write down the chain rule, and carefully set it out. Make sure you substitute it back in at the end as well. Yep. Which one were we up to? Oh, this one here, sine squared 2 theta plus 1. Again, it's the same sort of difference here. Yep, you're going to have u squared, this part, but it's really, that 2 is not really there. It's just written there, that's squared. So given it's u squared, the u part is going to be sine 2 theta plus 1, and obviously the other part is going to be y is equal to u squared. So writing each of those out, writing out the chain rule like we did before, derivative of u2, or u to the power of 2 is 2u. The derivative of sine 2 theta plus 1, again that's the k value, it comes out the front. Sine, the derivative is cosine, yep, and then obviously this stays the same, like that, yep. Cool, this one here. Oh, cool, this one's cosine cubed for theta plus 1. Again, should be no surprises from the previous examples I've explained. Yep. So again, this is going to be the same as u to the power of 3. So y equals u3, and u is going to be cosine 4 theta plus 1. Yep. Writing out the rule, derivative of u to the power of 3, 3 comes to the front, take away 1 from the power, 3u squared. We need to differentiate cosine 4 theta plus 1. K value is 4. It comes out the front, but remember the derivative of cosine is negative sine. So once that comes out the front, it's going to be negative 4 that comes out the front. Sine, and then obviously what's in here. Writing it out, multiplying this negative 4 by 3 gives you negative 12. Making sure you resubstitute in what u is. Again, when you go to put u back in there, remember when you're squaring cosine, you don't put it at the end. You write it after the squared, after the word cos. Yep. So it's just the way it's written. Again, last one, tan 3 theta squared plus 1. Cool. So hopefully by now we know that this is obviously the same as tan u. This is the u part here. So writing out what u is, it's 3 theta squared plus 1. And we've got y equals tan u. Writing out the chain rule here for this. Knowing that the derivative of tan u is going to be sec squared u. Yep, so I've written that out. The derivative of u here, you've got 3 theta squared plus 1. Remember the power gets multiplied by the value in front. It's going to be 6 theta, and take away 1 from the power, so it's just the power of 1. That becomes 0. Yep. Resubstituting in what u is, we get our solution there for that. Cool, these are going to be fun. Alright, last little bit. Again, it says find the y-coordinate and the gradient of the tangent at the points on the following curves, corresponding to the given values of theta. Cool, so here we've got y equals cosine theta, and they want to know what's happening at when theta is equal to pi on 4 and when theta is equal to pi on 2. So what we're going to do is, first of all, we're going to find out its corresponding, what it's going on when theta is equal to pi on 4. So let's do that. When theta is equal to pi on 4, obviously you're going to be substituting in pi on 4 into the equation. We get y equals cosine pi on 4. Cosine pi on 4 is 1 over root 2. Yep. So here we've got our coordinates. So it's going to be pi on 4 and 1 over root 2. That's the coordinates where we're going to find out what the tangent is at that particular point. So we need to find out what the derivative is of cosine theta. Good news is we are able to easily do that. It's negative sine theta. So once we know what the derivative is, we're going to substitute in this theta value here, and we're going to find out what's happening at the gradient at that particular point. So negative sine pi on 4 is equal to negative 1 over root 2. So that is the gradient at that particular point. Yep. So at the point pi on 4, comma 1 over root 2, the gradient is negative 1 over root 2. And again, you can do the same thing for this value. When it's theta is equal to pi on 2, we get y is equal to 0. So they're their coordinates. Theta and y coordinates. From there, we can work out what the derivative is when it's pi on 2. So substituting pi on 2 into the derivative, we get negative 1, and we can write it out in full there. I'm not going to spend any more time going through this one. Same process happens here, and you guys are happy to read through that and understand it. Alrighty, there is a summary of our fun notes that we've had the chat about. I would definitely be putting in these into your summary fun booklets. Yep. Cool. Enjoy the exercise. Bye.